Hello, this is a presentation for class CSE 530, Embedded Operating System Internals course. My name is Nikit Shah and I will be giving a presentation on Zephyr kernel components. So, first question, what is Zephyr kernel? The Zephyr kernel is a small footprint kernel designed for use on simple embedded systems like IoT, etc. The Zephyr kernel offers a number of features as follows. First, single address space. This combines application-specific code with a custom kernel to create a monolithic image that gets loaded and executed on a system's hardware, making the application code and kernel code execute in a single shared address space. The second point here is highly configurable. This allows an application to incorporate only the capabilities it needs as it needs them as per the specified quantity and size. Third point here is compile time resource definition. This requires all system resources to be defined at compile time. This reduces cost and it also increases the performance. Fourth point here is minimal error checking. This provides minimal runtime error checking to reduce cost size and increase performance. An optional error checking infrastructure is provided to assist in debugging during application development. Fifth point is extensive suite of services. This offers a number of familiar services for development. One is multi-threading services for both priority-based, non-preemptive fibers and priority-based, preemptive tasks with optional round-robin time slicing. One is interrupt services for both compile time and runtime registration of interrupt handlers. One is inter-thread synchronization services for binary semaphores, counting semaphores and mutex semaphores. One is inter-thread data passing services for basic message queues, enhanced message queues, and byte streams. One is memory allocation services for dynamic allocation and freeing of fixed or variable size memory blocks. One is power management services such as tickles, idle, and an advanced idling infrastructure. The Zephyr kernel supports a variety of device drivers. The Zephyr device model provides a consistent device model for configuring the drivers that are a part of a system. Each type of drivers is supported by a generic type API. Zephyr provides a set of device drivers for multiple platforms. Each driver should support an implementation based on interrupt rather than polling. Unless the specific hardware does not provide any interrupt, high-level calls access through device-specific APIs such as I2C.h or SPI.h are usually intended as synchronous. Thus, these calls should be blocking. Due to the fact that Zephyr provides two types of execution contexts that are task fiber on a microkernel, driver need to behave accordingly. For example, a nanokernel semaphore cannot be used when the context is a task. So, the include/device.h file exposes a helper API to handle this case transparently. No other means should be used otherwise. Device underscore sync underscore call underscore t provide nanokernel semaphore. Device underscore sync underscore call underscore init is used to initialize the device underscore sync underscore call underscore t type semaphore. This function will only be used since it is used for initialization. To perform a wait of operation on the relevant semaphore, device underscore sync underscore call underscore wait is used and device underscore sync underscore call underscore complete API is used to unblock the blocking function by releasing the relevant semaphore. Now, the Zephyr driver is based on several Zephyr components like GPIO, I2C, PCI, interrupt, SPI. Each component has a specific design and implementation. It is also necessary to know where and when these components are used. So moving on to the next few slides, I will be talking about the Zephyr kernel components, starting with GPIO. Okay, so GPIO, a general purpose input output, that is GPIO, is an interface available on most modern microcontrollers to provide an ease of access to the device internal properties. GPIO is used where input output is there has to be some interface between input and output, so there GPIO is used. API is used for GPIO interface in Zephyr kernel R. GPIO underscore callback underscore handler underscore T. This API defines the application callback handler function signature, whereas other APIs such as GPIO underscore pin underscore configure, which is used to configure a single pin. GPIO underscore pin underscore write is used to write the data value to a single pin. GPIO underscore pin underscore read is used to read the data value of a single pin. GPIO underscore init underscore callback helps to initialize a struct GPIO underscore callback properly. GPIO underscore add underscore callback helps to add an application callback. GPIO underscore remove underscore callback helps to remove an application callback. GPIO underscore pin underscore enable underscore callback GPIO underscore pin underscore enable underscore callback enable callbacks for a single pin. GPIO underscore pin underscore disable underscore callback disable callbacks for a single pin. There are some other APIs which are similar to these APIs for using a port, like GPIO underscore port underscore write and GPIO underscore port underscore read is used to write or read the write or read the data value to or from a port. So these APIs are handy and easy to use. Moving on to the next slide, which is I2C. I2C is a serial protocol for two-wire interface to connect low-speed devices like microcontrollers, EEPROMs, etc. Devices like microcontrollers, EEPROM, etc. APIs used for I2C interface in Zephyr kernel are I2C underscore configure, which is used to configure operation of a host controller. I2C underscore write. This API is used to write a set amount of data to an I2C device synchronously. I2C underscore read. This API is used to read a set amount of data synchronously. I2C underscore transfer. This API provides a generic interface to perform data transfer to another I2C device synchronously. I2C underscore burst underscore read API reads multiple bytes from an internal address of an I2C device synchronously. I2C underscore burst underscore write API is used to write multiple bytes to an internal address of an I2C device synchronously. I2C underscore burst underscore I have just covered that. I2C underscore reg underscore read underscore byte routine reads the value of an 8-bit internal register of an I2C device. I2C underscore reg underscore write underscore byte routine writes the value of an 8-bit internal register of an I2C device synchronously. I think there is one missing over here, but I would like to talk about it. I2C underscore reg underscore update underscore byte updates the value of a set of bits from an 8-bit internal register of an I2C device synchronously, and there are many more APIs which can be used for I2C interface in the Zephyr kernel. Moving on to the next one, interrupt. So we all know what is interrupt and where and how it is used. So an ISR is a function that executes asynchronously in response to a hardware or software interrupt. As we know, there are two types of interrupts, hardware and software, and it depends on the application and priority, and depending on that we need to know which interrupt we need to use. So ISR is basically a function, so when an interrupt occurs, the ISR function is called and the code inside the ISR function is executed. So basically a system call is an interrupt. So when you want to switch from user side to kernel side, there is a system call which is an interrupt, and because of that my execution will go to ISR and the code inside my ISR will get executed. Okay, the following interrupt related APIs are provided by IRQ.h. IRQ_connect initializes an interrupt handler. IRQ_lock is used to disable all interrupts on the CPU. IRQ_unlock reverses the effect of a previous call to IRQ_lock using the associated lockout key. IRQ_enable is used to enable interrupts from source IRQ. IRQ_disable is used to disable interrupts from source IRQ. IRQ is enabled. IRQ_s_enable is an API used to determine if code is running at interrupt level. I'm sorry about that. IRQ_s_enable is used to indicate if interrupts from source IRQ are enabled. K_s_in_ISR is an API used to determine if code is running at interrupt level. And there is one more. K_is_preempt_thread is used to determine if code is running in a preemptible thread. So these are all the APIs used for interrupt service routine. There are no other APIs apart from these, and these are very handy to use. And this is it. So there are many other components which I would like to discuss, but because of time constraint, I have to stop here. Many other components like PCI, SPI, which is very useful obviously depending on the application. So yes, talking about the components, these are the 5 to 6 main components which are used for almost all applications like Bluetooth sensors. mm, then for the project that we have done in part 1, we had to use GPIO interrupts, PCI, I2C. So yes, depending on that, we use APIs. APIs are obviously, as I have discussed, for different application. There are different APIs for writing, reading, locking, releasing. There are APIs. So finally, I would like to thank Dr. Yanhang Lee for the wonderful course assignments. It was a great learning experience. Special thanks to the TA Amit Rane for being there for every assignment and for everyone. Thank you.